So we'll take a step backwards real quickly, review what we looked at. So we were talking about acids and bases. In particular, what we were looking at is our potential acids. And we're running both of these reactions I tried to mimic. So when we talked about acids, acids were defined because they, what was our rule? Lost H plus in the course of the reaction. So if we look at that HCN process, it becomes CN minus. So to go from that acid to the other side, we had a loss of H plus, right? Okay, this applies to the formic acid, the HCOOH directly above it. It's the exact same columns. Okay, so in the process of reacting with water, that processes across. We also briefly talked about bases, and bases were the species that would accept H plus or gain H plus in the course of the reaction. So we're kind of using that gain and loss similar to what you probably did with your redox reactions. We talk about gaining and losing electrons, but now we're gaining and losing H plus. We could apply that definition to water just as easily, because if we look at what happens to water in the course of this chemical reaction, what happened? It gained H plus. So if we're looking at that species gaining H plus, we would call, we would call the species that gained H plus a base. We could then go through and look at the products of that reaction, and if we flipped those on their head and looked at the reverse, because we're in equilibrium 152, all that fun stuff, we could go through and we could equally label the other side of the equation as base and as acid. We discussed that that's problematic because if we're now going to go through and talk about what's the acid, we've got two things labeled acid. So we added an extra term into this. That extra term was conjugate. The conjugate typically applies, how do you spell wk? Okay. Typically applies to the product side of the equation, though it technically can be applied anywhere. Okay, so we could refer to water and H3O plus as conjugate partners, okay, conjugate base and acid, okay, so they're conjugate pairs. Typically when we're looking at a chemical reaction, if we're asking for the conjugate base, we're talking about the species on the product side that would act as a base when it becomes the reactant. Kind of makes sense? Okay. The place where we ended was talking at pH. Well, why would we want to talk about pH? Okay, the point of pH is trying to take this information that we're looking at here, say these two acids, and come up with some way to rank them. Because if we talk about acids, you might go, oh, well, acids are dangerous, they're corrosive, they melt my skin, they're dangerous. Okay, well, if they're dangerous, how dangerous are they? Okay, so we talked about some examples. If you stuck your hand in battery acid, that's a problem. But if you stuck your hand in lemon juice, that's not a problem. But they're both acids, okay, so what's making them dangerous, what's making them reactive? Ultimately, it's the production of that H3O plus, okay, or the H plus. Right? And if we're talking about the battery acid, it's because it's producing a much higher concentration of the H plus than our lemon juices. So we could go through and now warn people, not just worry about acids, but worry about the production of H plus in the course of this reaction. That generates all sorts of problems. Okay? I think I referenced little Timmy. I've got a friend named Tim, so I just make fun of him in class, okay? Because he never looks at the videos, so it's okay. And I don't think anybody's named Tim in any of my classes, so I think it's also okay this semester. Okay? So little Timmy doesn't know anything about what's going on with the periodic table. He doesn't know what hydrogen is. He doesn't know what water is. He doesn't know what H3O plus means. What's the positive charge? We had a whole conversation of why things were positive and negative. Okay? And you're advanced chemists. Little Timmy isn't going to know jack about any of that. We need some other way to present this information to him. Okay? And so that's where scientists said, okay, how can we repackage the information about the concentration of H plus and turn it into a system that is relatively easy for everybody to understand? Okay? And that's where we rely on mathematicians and say, hey, mathematicians, I've got this weird big number. Can you make it look pretty? The mathematicians go, yes, of course we can make it look pretty by using this mathematical operation that some people understand and I don't. Okay? And we get the negative log of the H plus concentration. And we don't even need to explain that to people. All we need to go through and explain is that if we look at the pH, we can convert that system around and set us up with a way to represent the concentration of H plus on a scale from 0 to 14. That numbering scale is now relatively easy for us to manipulate and describe. Okay? And if we push on it, it's not even really 0 to 14, it's really just 0 to 7 and 7 to 14. Okay? Because the center point on this, our 7, goes all the way back to our universal solvent, water. And since water makes up everything, that's going to be the most likely scenario that little Timmy is going to encounter any of this chemistry, is those reagents in water. Okay? So we don't have to explain anything really that's outside that realm. Could we have negative pHs? Yeah. Okay? Can we get pHs really above 14? And technically negative and above? Kind of not really. Okay? The problems that we encounter there are, those are now outside the realm of the chemistry possible to water as the solvent. So to understand what's happening at those extremes, we get rid of water and we move to other systems. Okay? Do you want to get rid of water yet? No? Then don't worry about those. Okay? So what we're primarily concerned about is how we navigate on this scale. Okay? Water is, again, our 0 point, okay, which we've defined as neutral, or our safe space, if you will. Okay? And if we look at the concentration of H plus that comes out of it, it comes in as negative 1 times 10 to the negative 7th, okay, moles per liter of our H3O plus. The lower on that scale we get, the higher the concentration becomes. We're going 10 to the negative 7th up to 1. Okay, powers of 10, what happened to the power of 10? It was such a large power of 10, we got rid of it. Okay? And we go the other direction, it gets smaller. Okay? So our pH scale is just a way to convert and sell the concentration of H plus to the general public. Okay? Since you're now chemists, you're responsible for that conversion process, which means when you go through and run your chemical reactions and determine the concentration of H3O plus, okay, you're also going to be now expected to tell us what the pH is, so that you can now sell that to the common populace. Conversely, you will also have to take the common populace information of pH and convert it back into H plus. Kind of makes source sense? Okay. How do we go from pH to concentration of H plus? So if I give you a pH of 2, how do I get the H plus? That equals the negative log, conveniently, of our H3O plus.
You put the pH at a 10 base.
Okay. We do the anti-log, which is a 10 base for people that, like me, that don't necessarily understand that. It's not just a standard 10 base. We also have to take into consideration the minus. So we get our concentration of H3O plus is now equal to 10 to the negative pH. Okay? That allows me to now kind of interconvert back and forth between those. Hopefully that was something you already knew theoretically from your math classes. Okay? So if we go back to water, okay, you will have probably noticed that water showed up both in the acid definition and in the base definition, because what can water act as? Both an acid and a base. Okay? So if I drop water and react it with water, I could go through and say water 1 acts as an acid and water 2 acts as a base. There is no way to differentiate between those two molecules. Okay? But ultimately, all we're really trying to say is that water does both of these things. Okay? Acts as both an acid and as a base. If we go through and now consider, should this reaction be product favored or reactant favored when at equilibrium? It's a blue box. Take a hot second to discuss at your table. So what do you think, reactant or product favored? Okay. To decide that, we have to run through our calculation, right? Take our concentration of hydroxide and the concentration of H plus at equilibrium. What's their concentration? Do you know what they are at equilibrium? Okay. And that's where several of you should probably be shaking your head, no, I don't know that, Mike. I don't know that at all. Okay? And that's where I can say, well, that's not true. You do know that. What's the concentration of H plus at equilibrium? 10 to the negative 7. Okay? That was the whole point of our pH scale. Okay? Why is that valuable? So you could plug that in and be like, well, I don't know the hydroxide concentration. Do you? Do you really not? Where did the H plus come from? From the water. And in the process of forming H plus, what did I also have to form? Hydroxide, which means if I know the H plus is 10 to the negative 7, I know the hydroxide is also 10 to the negative 7. So now when I go through to calculate my K, I take 10 to the negative 7 times 10 to the negative 7, and I get, don't shout it out all at once. It doesn't get picked up by the microphone very well. That's so when people watch it at home, they're like, oh, that class is really active. 10 to the negative 14. What does that mean? Is that product favored or reactant favored? That's heavily reactant favored. Okay? Does that make sense? Okay, what happens when you dip your hand into water? It gets wet. That was pretty boring. But if I dipped my hand into a concentration of H plus, what would happen? Potentially melt my hand off. Okay, right? And so when I stick my hand into water, does it melt off? No. Why not? What's the concentration of H plus? Next to nothing. Okay? So very few products come out of this chemical reaction. Kind of, sort of? Questions? What? Come back here. Nope, come back here. So pure water is going to generate those small concentrations. We just talked about them. We're looking at that pH scale by definition. That's at equilibrium. Okay. Neutral water comes in at 10 to the negative 7th molar for our H3O plus. And if it's H3O plus is 10 to the negative 7th, the hydroxide will also have to be 10 to the negative 7th because they're tied to each other through the chemical expression. That means our pH comes in at 7. That also means our equilibrium expression for water is K equals 10 to the negative 14th. That can become such an important equilibrium expression that what might we want to do with it? We might actually go through and name it. Instead of just saying it's the equilibrium constant 10 to the negative 14 and our hydroxide and our H3O plus, trust me, it all says that over there. I might add an extra layer of information to it. I might add a W next to the K because that's referencing come on. Water, because water begins with the letter W. So you'll see KW float around. KW is now a constant for water, 10 to the negative 14. Okay? Technically, it's a constant when? (25°C), our room temperature. Because if we change the temperature, what happens? We change K. Right? That goes back to that previous unit. So when we're talking about all of these acid-base reactions, I'm going to hazard a guess, I haven't looked closely enough at them, but I'm going to hazard a guess that all of them are run at 25°C. Okay, we're going to maintain that temperature all the way through. Kind of, sort of? Okay. So, if we have a pH scale that goes through and converts things across, we could also go through and do a pOH. Okay, so P just means take the negative log. Why? Because we're trying to convert these goofy powers of 10 into a number that's more reasonable for us to understand and manipulate and deal with. So I can take the P of anything. That sounds kind of fun. Okay? So I can do the pH and I can do the pOH. Anything I want, I can take a P of. Okay? When we're talking about water, we can say our pH plus our pOH must equal 14. Why? Well, that's coming out of all of these expressions that we've defined for the system of water. So all of these equations at the bottom now become valid as long as we're dealing with water. Okay? So if I know the pH, I can calculate the pOH really quickly because I know it's based off of that scale of 14. And because I know the H and the OH are kind of opposites within this system. As I increase that H plus concentration, the OH is going to have to decrease to account for it. Okay? So you get a whole plethora of equations that immediately just kind of fall out of it, if you will. Okay? How many of you have heard of the pOH? Okay? Only a few people. Why only a few people? Because we prioritize acids over bases, because our exposure to acids is much larger than it is for bases. Okay? So that just comes from scientists trying to protect the public, potentially, as much as possible with these scales and these ranking systems. Okay? So if we go through and look at two examples here, soda has a pH of about 2.5. What are the concentrations of H3O plus and OH minus? Would we expect this solution to be acidic or basic? All right, we got the same thing, but now we're going to look at it for orange juice at 3.5, except we got a slight twist in the question. How many times lower is the concentration of H3O plus compared to the soda? Which is more acidic? Okay, these are both blue boxes. We've got calculations that theoretically can be run for both of these. You should start working on those, talk through with your table to figure out what's going on, see what you can come up with. So we could go through and set up our calculations using our formulas. There's a variety of different formulas that you could go through and manipulate. That mouse cursor is bugging me. I don't know if I can move it. So for our pH, 2.5 is going to be equal to our negative log of our H plus. So to get the H plus concentration, we've got 10 to the negative 2.5. Right? If we go through and figure out our OH, we could go through and use one of the calculations that relates the H plus to the OH minus through the KW and deal with powers of 10. Ultimately, I don't really like powers of 10. So what I would do is deal with the POH conversion with 14 minus 2.5. And I just realized I'm not very good at subtraction either. 11.5?
Yes.
Thank you. So when I figure out my concentration of my hydroxide, I'm following the exact same pattern that I have on the other side, 10 to the negative 11.5. Kind of makes sense? Okay. Is the solution acidic or basic? Acidic. How do you know? Not you, because you said it. Cool. If you know your pH scale, if you're under that 7, you know it's acidic right out of the gate. Okay. You don't have to look at the actual concentrations of H plus and OH minus. That was the point of the pH scale, is to give us a ballpark idea of where we're at on that system. Kind of makes sense? You could equally go through and compare your values for your H plus concentrations. Just suddenly dawned on me as well that if we're going to enter this into Alex, I would bet Alex is going to have a problem with it, you saying the H plus concentration is 10 to the negative 2.5. Right? And I might also have an issue with that on an exam. I don't really know about that. Okay? So theoretically what you should do is enter that into the calculator, 10 to the negative 2.5, and it's going to spit out a number. That number is what you should be writing down for your H plus concentration. Does that make sense? I used to know how to do that well. I don't know how to do that well. Does someone know that number? Say again? That was for the H, that has to be for the H plus. Okay. We could deal with sig figs. I don't think we've ever worried about sig figs. Ooh, in lecture or on the quizzes, Alex might care. So pay attention to that. Which is extra fun because the mathematical operation you're running is a log, which then means you have a whole new set of sig fig rules. And I literally do not know what they are. Yeah, perfect. Exactly right. I'll try and figure out what those sig fig rules are for entering into Alex. Where I would start is if it has 2 sig figs, I report 2 sig figs and hope for the best. So I look at that at 2.5. So I would report my answer to be 3.2 and hope for the best. Okay, currently. Okay, that's because I literally don't know what the sig fig rule is with logs. So all you got to do is look it up to figure out what it is. I'll try and get that figured out from a colleague because I know I've talked to a colleague about it. And he's like, yeah, the log sig fig rules are awful. That's about all I know. Okay? Whether Alex follows them is a whole nother issue. Okay? Hydroxide, we do the same thing, enter it in your calculator, spit out whatever number it spits out. Okay? Again, I'm going to trust you to figure that out. If we look at the pH of orange juice, how many times lower is the concentration of H plus compared to soda? Why is the concentration lower? Because the pH is higher. Does anybody notice a potential area of confusion with that? Why is it lower? Because the pH is higher. So you're going to have to deal with this high-low system and how you're comparing. Ultimately, what's that coming back to? We've referenced it a couple times this semester. It's coming back to that minus sign in our calculation. That minus sign is what's screwing up the high-low system. Okay, so be aware of that minus sign messing with your interpretations of high versus low. Okay? So how many times lower is our concentration? 10 times. But it's a difference of only 1. Why is it 10 times, not 1 time lower? Well, 1 time lower would not be lower, right? Times by 1 wouldn't change it, so that doesn't make sense. Why is it 10 times? How did we go from 1 to 10 with a pH difference of only 1? It's not equals pH difference.
It's to the power of 10.
Remember, pH was a negative log. This is the negative log of 1. Whoops, not of 1. Negative log of x equals 1. That x is what you're solving for. That's your 10 times. Okay? Kind of makes sense. Which is more acidic? The soda is more acidic because it has a lower pH. More acidic, lower. More, low. We got to watch out, again, dealing with that inverse flip in it. Make sense? Okay. So, Ka is the equilibrium constant for an acid reacting with water. Okay? So we're going to hear lots of Kas. We already heard a Kw. We'll hear Kb. We'll hear Ksp. Ultimately, all of those extra little symbols that we're tacking on don't change the underlying meaning. If I want to look at the equilibrium expression for this reaction, what is it? Well, it's the same as it is for all reactions. It's the product over the reactants. So the product, in this case, would be Cn minus times the concentration of H3O plus divided by the concentration of HCN. Why do I not include the water? It's a liquid. Technically, it's already included. It was a constant. Its concentration isn't changing, so what you did was took that constant and folded it back into K, which is why we do not include liquids or solids within a K expression. Their concentrations stay constant, and so we fold them into the K constant to begin with. So this is our equilibrium expression. Why do I have to call it a Ka? First and foremost, I don't. Okay? I can call it a K. It's perfectly acceptable to do that. Why might I call it a K or a Ka? I want to specify that I'm talking about the equilibrium constant for an acid. How do I know I'm talking about the equilibrium constant for an acid? Because we wrote the A next to it. Or What is H3O plus? That's our acid. Okay, so if you see Ka, that's an immediate tip-off that we're seeing H3O plus show up in our numerator. Okay? Okay, our acid-base reactions, if we talk about time and kinetics, okay, typically we don't have to worry about time and kinetics because the acid-base reactions happen very, very, very fast. Okay, so you're looking on probably sub-millisecond timescales. I mix them, done. We're already at equilibrium. Okay, that's one of the things that makes acid-base reactions really nice overall is that you don't have to wait for them to do what they need to do. They just do it, you're done, you can now make your observations. Okay, which is one of the reasons why we tend to study them a lot, because we get fast results. We get to this equilibrium very, very quickly. Right? Yeah. Questions? Okay. So, blue box, what do we notice about the pH of different 1 molar acid solutions? So we've got a whole bunch of acid solutions. By a whole bunch, we've got 4. We're showing a Ka, we're showing an H3O plus, and we're showing a pH. What do you see about the pH for equal concentrations of these acids? Okay, so they change. But here's a good blue box question. Now you can talk at your tables.
More to the right.
Okay, so this was clearly too easy because you guys talked about it real fast and then you started talking about other things. Okay, so why? Why did the pH change? Dude, you all talked about it. Come on.
Concentration decreased.
Concentration of H plus changed. Why did it change? So if we're looking at this, okay, our pH increased, right? Why? Because what happened to our H plus? Okay. Decrease, we got that increase, decrease thing we got to watch out for again. But why? Why did the H plus concentration decrease? You're not wrong by saying it's getting more basic. The issue I've got with that is that if we start to go through and say things are getting more basic, what does that sound like is happening? I've got lots of hydroxide around. Are we talking about lots of hydroxide? No, these are still all on the acidic side of it, so we're still looking at H+. Shifting your focus, not incorrectly, but shifting your focus to now talk about hydroxide in an environment where H+ is dominant can get a little bit weird. Okay, and it can lead to some bad connections. Why is our H+ decreasing?
Because they're more reactant favored.
Okay, so you kind of skipped over the step that I would look at is what's happening with our Ka. Well, the Ka decreased. And if the Ka decreased, what does that mean about your reaction? I hate including H2O, just for the record. Stupid water. Okay. If we looked at our equilibrium, we're getting more reactant favored. Okay, so cool, I like all of that. Let's add some more language into that. What does that mean about the acids themselves?
They're reacting less with the water.
They're reacting less, okay? And in all of these were acids, and if they're reacting less, they're producing less acids, which then means they would be, there it is, less acidic. So what we're looking at is the relative strength of each of those acids. So we could now go through and rank acid strengths based off of looking at our H+ concentration, our pH concentration, or the Ka. Where we have to be a little bit careful on ranking based off of all three of those characteristics, right, is that ranking was dependent on one very, very important thing all the way at the very beginning of the question. they all started as equimolar solutions. Okay? That's why I can look at the pH. That's why I can look at the H plus concentration. Okay? Because those are raw outputs. But if I change the concentration up here, is that going to change my pH or my H plus? It will. Okay? If I increase my hydrocyanic acid, instead of being 1 molar to 6 molar, I'm going to produce more H plus, which means my pH is going to drop, increase, drop. I said that right. Okay? So the only reason I can look at pH and H plus and rank acid strengths is because I'm looking at an equimolar solution. What stays constant regardless of the concentration? The molarity is the concentration. We're talking about literally changing that. So the molarity is always going to change on us. What stays constant? Constant. Not the rate constant, the equilibrium constant. I can change the concentration of my starting solution. That's going to mess with the concentration in the pH. What is it not going to mess with? The Kas. Which means I can rank acid strength based off of the Kas always. I don't have to worry about, well, what was my initial concentration? Okay. The initial concentration is effectively the product, the end result of what that Ka is doing at that concentration. Okay. But the Ka is by definition a ratio. That's going to help me to determine which of those were stronger or weaker acids. Okay. The Ka is a normalization system. Concentrations are raw data. So Kas become very powerful to go through and rank strengths. H plus or pH can be really, really questionable. Okay? Kind of, sort of? Sure, it's a blue box. Why not? Okay. Write the reaction of acetic acid with water and write the equilibrium constant expression as a Ka. So lots of theoretical questions could come up out of this. I'm going to throw a little bit of shade for a second here. I see people writing the question. You shouldn't write the question. Why should you not write the question? It's literally already written for you. Okay? I saw people writing the chemical reaction out. You don't need to write the chemical reaction out. Why not? If I'm looking at a Ka, what does that mean shows up in my equilibrium expression? I have H3O plus, okay, and then I would have the conjugate base. I know the conjugate base needs to be negatively charged. Because it's the conjugate base, I need to remove a hydrogen. So let's remove a hydrogen. Okay, so CH3COO minus. I removed a hydrogen. What shows up in the denominator? The starting material, CH3COOH, done. Well, but I need the chemical expression to figure out what the reactants and products are. Maybe, okay? And that is a valid kind of statement for you to go through and walk through and say, but I need that. That's okay. You can start writing that out and start processing that, okay? But one of the things that's going to come up out of that is going to be a more complex question, because when you go through to write that out, what you're starting to do is focus on the structure, okay? For the record, I love that you're focusing on the structure. That is phenomenal. That's lovely. Except that when we go through to write out the equilibrium expression, are we writing out structures? No, we're writing out chemical formulas. And for the most part, our chemical formulas hide all information about structure. These formulas that are provided here are slightly better. They have some information about the structure behind them. Okay? But again, I would make the blanket statement that if you're going to talk about structures, you should talk about structures in which case we're not doing equilibrium expressions. If you're talking about equilibrium expressions, you're going to deal with formulas because you don't want to draw out the structures in those, which means just draw out the formula, which means who gives a flying rat which hydrogen you get rid of. Okay? Should you care? Hell yeah, because it's important. It's neat. It's fun. We like that stuff. Okay? How would we decide? Well, we could look at that structure. I'm just going to go straight up from this. I know, non-standard, but I don't want to draw it out again. Okay? We're going to form the H3O+, put that all the way up at the top, and then we're going to have to form some species in between where we've gotten rid of a hydrogen. Well, which hydrogen should I get rid of? Should I get rid of the hydrogen that's connected to the carbon, or should I get rid of the hydrogen that's connected to the oxygen? Okay. What this is ultimately going to come down to is a discussion on stability. If we're going to remove the hydrogen that's connected to the oxygen, what happened? What did we remove? Don't tell me hydrogen, do better. Just because I suck doesn't mean you need to. What did we remove?
Proton.
We removed a proton. We moved a positive hydrogen. How was the hydrogen, that positive hydrogen, connected to the oxygen? Through a bond, right? That bond represents 2 electrons. If I take H plus with no electrons, where are those electrons now? On the oxygen. So if we were to add some more information back to our structure, we'd be saying we have a lone pair. I don't know that I color-coded right. And that oxygen becomes negatively charged. Or we would have gone through and done the exact same thing, but we would have done it to the carbon. Whoops. And so we would have the lone pair now on the carbon instead. And if that carbon picks up that lone pair, what charge does it become? Negatively charged. You're like, well, what about the other 2 hydrogens that are going to produce the exact same red structure that I've got? Or sorry, I guess I should have shown it as a purple structure. Okay. Well, which of those 2 is more appropriate? Is it better to remove the hydrogen from the oxygen or from the carbon? Well, ultimately, the hydrogen isn't going to dictate that. What's going to dictate that is what was left over. Would I rather have a negative oxygen or a negative carbon? I would rather have a negative oxygen because oxygen is more electronegative. What does that mean? The hydrogen I should remove would be the hydrogen that was connected to the oxygen. But if we write out a chemical formula, does the chemical formula tell us the connectivity? Generally speaking, no. Okay? There are certain formulas that do. We just happen to be looking at a formula right now that does provide that context. So if you're looking at a chemical formula and there's a whole bunch of hydrogens, deciding which hydrogen to remove can be a little bit tricky. If you don't know, remove them both, look at the resulting structures. Now think about where that negative charge is located. Is it better in one structure versus the other? Okay? That's the best approach. The other approach is what is likely described in your textbook. You look at the atom that the hydrogen is connected to. If it's more electronegative, take that hydrogen. Okay? If it's bigger, take that hydrogen. Okay? If it has, I think they do, what do? More oxygens, take that hydrogen. If it's near more halogens, you take that hydrogen. Okay? And I'm balking at that because I really don't like how Gen Chem describes it, and the broader context of it is something that you would discuss in a lot more detail in organic chemistry, but that's looking at structures, which you aren't. So it's trying to find that balance between how much information do we give you without giving you so much that we have to give you even more. Kind of, sort of.
So if we're just given a chemical equation, we don't need, and like we're on a test, we don't need to draw the Lewis structure out and figure it out then?
Nope. Okay. My bet, since there's enough structures kind of showing up, is I wouldn't be surprised if you're going to see some questions in Alex, okay, where you see a more complex structure and say which hydrogen is the most acidic. And what they're going to base it on, electronegativity.
Gotcha.
Okay. Does that make sense?
Yeah.
Okay? In 152, how do we decide which hydrogen was more acidic? How would I decide which hydrogen was more acidic? We just said it. How did I know a hydrogen was more acidic? What would I need to look at? Concentration, we said, was dangerous because concentration was heavily dependent on the starting concentration. So let's not look at the concentration, let's look at the equilibrium constant. So what I would go through and do is look at the equilibrium constant for a hydrogen connected to an oxygen versus the equilibrium constant for a hydrogen connected to a carbon. Right? I could then compare those equilibrium constants to each other to decide which one was more or less. Right? I would argue that's very painful because I now have to look up and quantify all of that information, and I don't like doing quantification. Right? But that's also why I don't teach 152. Yay! And yet here I am. Right? Organic chemistry takes all the quantifications that are there and says, can we do this without quantifying it? Can I create rule sets that allow me to navigate it without quantification? And yes, we absolutely can. But that requires some more interpretation of structure, which we probably don't want to get into. Kind of, sort of? So we get to float in a happy, unhappy gray area. Go back and reference your equilibrium constants, and that's how you're going to navigate it. When it comes to actual questions within a quiz, we'll have deeper conversations if I know more. Okay? Acids and bases, if we look at their overall performance or what they can go through and do, both of them have the ability to denature proteins. Denature proteins means we destroy the structure and it falls apart. Okay? We looked at some slides and some images with proteins. Proteins are these big long chains that are all folded up into this neat little mess, right? Okay? That neat little mess has particular chemistries. If we go through and add an acid or a base, that acid could go through and it could protonate. It could put hydrogens on different parts of that protein backbone. And if it puts hydrogens on that protein backbone, it's going to change the intermolecular forces. If the intermolecular forces change, the whole structure tends to fall apart. Okay? That falling apart process is what's known as denatured. It has now lost its function, it's lost its proper structure, which is why that function disappears. Okay? So you could go through and look at varying systems to explain it. I think what they're trying to show in here is a nice little zoom in of glutamic acid and lysine. And if we go through and add hydrochloric acid, what happens? The hydrochloric acid will protonate that oxygen. Okay? That oxygen is now no longer negatively charged. Because it is no longer negatively charged, its connection or desire to be neutralized by the positive of lysine has all but gone away. Which now means those two amino acids that were hanging out real close to each other have no reason to talk to each other anymore. They fall apart. Once that bridge has now been lost, and that happens enough throughout the structure, you no longer have a proper folded structure. That's where all your functionality disappears to. Bases can do something similar. The bases are hydroxides. They could come through and they could remove the hydrogen, say, from lysine. If we remove the hydrogen from the lysine, it's no longer positively charged. It changes its interaction with the negative. And again, the protein can fall apart. Kind of, sort of. Bases do some extra fun stuff, okay, particularly when it comes to fats. Let's just say fats. Okay? Where do we see fats? In your belly, Mike. Thanks, jerks. Okay? Fats make up cell walls. Okay? So if you look at a cell wall, those are all different forms of lipids and fats. We also have fats elsewhere, like my belly, but beside the point. Okay? But the cell wall is also made up of a whole bunch of fats. And if I add a base to that, that base can react with the fat. Okay? It's doing a much more advanced chemical reaction. It's busting into organic chemistry. This is no longer the removal of a hydrogen. This is that hydroxide inserts itself effectively between our red and our blue structures. Okay? Why is that a problem? Well, that takes the one structure and turns it into 4. It's not balanced here. Okay? Why is that a problem? Well, if your cell wall doesn't have that one structure and instead has the 4, guess what those 4 things do? Create holes. Do we want holes in our cell walls? No. And generally what happens is we get holes and now the cell dies and falls apart. How do we know this is happening? It creates that carboxylate salt. That carboxylate salt should be kind of interesting and familiar to you because you probably used that the last time you went to the bathroom. You hopefully used that the last time you went to the bathroom. That carboxylate salt is soap. Okay? So one of the common observations that people will get with bases, they go, oh, it's slippery. Why is it slippery? It's eating through your cell walls, man. Okay? As it's eating through your cell walls, it's making soap of your skin. That's generally a bad thing. Okay? So soaps tend to be slippery. Acids tend to be sticky because it's changing those intermolecular forces and it tends to kind of increase the attraction between things that shouldn't be attracted to each other. Okay? Okay. So Ka, and pKa. Did we talk about pKa? No. What did we talk about with P? This is hilarious. Sorry. Such a 5-year-old. We talked about pH. Was that all we talked about? We said POH because we said we could do a P of anything. Okay? If we can do a P of anything, can we do a P of a Ka? Yeah, why not? We can do a P of a Ka. Why would we want to do that? Well, what's an example? Give me a number for a Ka you've seen. Unfortunately, there's not one up there. I could be like, just read it off the slides. If you look back at all the Ka values you saw, we're looking at powers of 10. Right? Lots and lots of powers of 10. Do we like powers of 10? Okay. People are like, oh yeah, I totally like it. Talk to anybody younger than you. Okay. Or maybe less educated might be the other direction to go. What's a power of 10? Okay. Powers of 10 are not things that human brains do well with. This is why we had to convert the H plus concentration into a pH so that we could get to that 0 to 14 scale. That was the whole point. And if we go through and talk about ranking acids and look at the Kas, they're all in powers of 10. Well, the powers of 10 are challenging to deal with, and if we use the P scale to deal with our H plus concentration, why can't we use the P scale to deal with our Ka? We can. And so what we'll end up doing is converting our Kas into pKas. Those pKas are now going to hit on a scale system that replicates-ish pH. Okay? One of the things you'll see that comes out of the pKa scale is it's not confined to 0 to 14. The pH scale is confined to 0 to 14 because water and water alone. When you shift to the full-on Ka scale or the pKa scale, it's not necessarily in water, which is why you can get Kas that are really, really, really low. Okay? You can get them pushing into the negative range. And that happens if you have a Ka that is really, really, really large. Okay? A Ka that's larger than 1 generates a pKa that is less than 0. Okay? So a big number makes a small number. Damn. So we've got another of these inverse relationships that we're going to have to process and keep straight. Okay? Is that easy for you to do? Okay, some of you are like, oh yeah, it's totally not. Okay, it's a personal choice. I would argue it's not easy at all for me to do. And so what I would immediately try and go through and do is copy this shit down onto, onto a note sheet that I'm allowed to have on an exam that would allow me to just say, what's that relationship, so that I can nail it down without having to think about it. Because I'm pretty sure left, right, up, down, turn around, all that stuff is going to get screwed up in my brain during a test. I would rather have it written down in front of me. Okay? So if you're even borderline on being able to deal with those relationships, you should nail those relationships down really quickly. Strong acids have large Kas, which means they have small pKas, which means they're product favored. Okay? To this day, when talking about strength of acids and ranking pKas, I will write out K equals products over reactants and translate that, plug in random numbers for my products and reactants. Products being 1,000, what does that mean my pK is? And I'll punch it into the calculator because I'm too brain numb to be able to memorize that constant for anything longer than a few seconds. Okay? So if you're allowed a note sheet, I would highly recommend that you got this down. The examples, up to you. You can decide whether you want to keep it or not. Okay? The big lesson that is going to come back and haunt you, the larger the Ka, the smaller the pKa, the stronger the acid. That statement is going to come back again and again and again. That is, if you're any kind of pre-health profession, okay, or chemistry profession. Because that's going to show up in organic chemistry. It's also going to show up in biochemistry. Okay, heavily. And it won't be just, well, I have to memorize that. You'll have to apply it 6 or 7 times in a single question. Okay? So very, very important to have that nailed down. Ideally memorized. You may not be there yet, so have the slide. Okay? Strong acids at equilibrium are product favored. So what we're talking about is looking at HCl reacting with water. In the presence of water, the hydrogen from our acid quickly donates to our water to give us H3O plus and the chloride ion. Okay? What happens to the Ka? The Ka is going to be wicked huge. Why? Because HCl is a strong acid, and strong acids, by definition, completely dissociate. Okay? How do we see that manifest? We see that manifest because we're seeing a Ka that is wicked huge. And because it is wicked huge, that turns our pKa now into something really, really small. Side note, hooray for me, this is what I said the pKa was for HCl like 2 days ago in OChem. I didn't remember it. I was like, yeah, I'm just going to say it's 6, -6. And I was right. Look at that. Excitement. Okay? When we go through and look at a weak acid, okay, the weak acids are reactant favored. So if we go through and look at these, this is supposed to represent, okay, our starting acid. Okay? No, we don't really see any of the starting acid over here. Why? Because it's a freaking strong acid. It completely dissociates. I don't see any of it present. When I shift to a weak acid, okay, I will see it present. The hydrogen is still connected to that conjugate base. It did not react with the blue water, so there's water molecules all the way around, to produce the H3O plus to any large extent. We're seeing a small ion floating around out of this. Okay. What does that mean? My Ka, my products over reactants, is going to be small, 10 to the -5. And my pKa is going to be larger than my strong acid. That's about it. Hooray, we're done. Sorry, that was a joke. Connoisseur? Bad taste. Okay. So which is a stronger acid, formic acid or hydrocyanic acid? Calculate the pKa of each acid. So we're back at this table. I already started to preference this, and now you can go through and process this information out. Talk to each other at your tables, figure it out. It's one of the reasons why I hate lectures like this, particularly because I'm a freaking idiot and can't hold it in my head. So as I walked through, we got several people being stronger acid, larger, and I'm still going to screw it up. The larger Ka is the more acidic. I was like, how did you even, I know we just said that, but I don't have it. Right? Again, what I would write is K is products over reactants. If I'm looking at a Ka, it's H plus, whatever the product is, over whatever the reactant was, but I'm talking about that H plus concentration. If I'm talking about something that is a stronger acid, I should expect a larger concentration of H plus, which means my Ka is bigger. Right? So I come to the exact same conclusion as you, except I'm too dense to keep that in my head and have to derive it each time. Kind of makes sense? So if you have that equilibrium stuff handy and at the back of your head, you can derive all of these relationships and you don't have to have them memorized. Okay? Or theoretically on your cheat sheet. It just takes a little bit more time. So with that said, we can now go back and look at the Kas of our formic acid and our hydrocyanic and say which one was bigger. The formic acid was bigger. Right? It's that power of 10. That power of 10 can be tricky to deal with, which is why we can convert it into our pKa by taking the negative log. Trusting your class, we got the negative log of formic acid coming in at 3.71, and for hydrocyanic, 9.21. The smaller the pKa, the stronger the acid. Everything checks out. Make sense? Easy? Cool. This is where I would usually say, and now for something more difficult, but I genuinely don't remember. So, strong acids, you're looking at pKa's much larger than 1. Okay? My personal statement, and I know this goes against Dr. Schneblin's philosophies, okay, would be to tell you that you should memorize your strong acids. Not their pKa's, not their Ka's, any of that. You should memorize it. When you see HCl, it's a strong acid. When you see H2SO4, it's a strong acid. You have that memorized. Okay? And the reason being is it makes it easier to manipulate and do other calculations. Okay? So when you see a question of rank these acids and you see H2SO4, boom, strong. It's already at your max end. And if you see something that's not one of these, you know you're going to have to now worry about dealing with your Kas. Kind of make sense? Okay. If in that same question you see H2SO4 and HI, well, now you're kind of screwed and you have to look at pKa's to figure out the difference between them. Okay? Because you don't have the rule sets to be able to manipulate structural information giving you that ranking difference. So you would actually go back to your Ka's to evaluate which one was stronger or weaker. Does that make sense? So just because it's a strong acid doesn't mean it's the strongest. You have to worry about that kind of ranking system, and that's always going to go back and look at your Ka's or your pKa's, depending on your preference. Okay. Most people and most books will go back and reference pKa's because, again, they're easier numbers to manipulate. We don't have those powers of 10 to deal with. Kind of, sort of. All other acids are considered weak acids, okay? Which is technically a bit of an overstatement because there are other strong acids. Why do we not make you look at those? You don't see them very often. Okay? So the strong acids that you're going to see are the ones listed up here. Okay? The other strong acids or stronger acids than these are so strong there's really no reason you would ever come in contact with it, so we aren't going to discuss those. And if you happen to be probably a chemical engineer, maybe you would deal with those stronger acids if you were doing semiconductor syntheses. Okay? Kind of, sort of? So, if you know you have your strong acids memorized, as soon as you see something that's not that, you know it's a weak acid, and that means you're going to have to deal with your K expressions. So why are strong acids strong and weak acids weak? Okay? It has a lot to do with your K expression and your delta Gs and all of that fun stuff. I would argue that why they're strong and weak has to do somewhat with the stability rules that we develop, but ultimately they're just observations of our calculations. And when we go through and look at a strong acid, we're getting a K that's really large. So what would that visually mean? That means our products are very, very low in energy. They're very stable. And our reactants are very high in energy. That's resulting in a very exothermic reaction. Think back to safety. If you're going to mix a concentrated acid with water, how do you mix them? Do you add the water to the acid? or do you add the acid to the water? Acid to water. Why? This is why. When you add that acid to water, you're going to run an acid-base reaction. It's very exothermic. That strong acid wants to become that conjugate base. It produces lots and lots of heat. And if you add the water on top, that chemical reaction is happening at the bottom of your tube. Why is that a problem? It's going to produce heat at the bottom of the tube. And if it produces that heat at the bottom of the tube, it's going to turn it into a gas. But it can't get to the gas phase easily. It has to pass through the liquid you just poured on top, which means explosion. So we add the acid on top so that when it creates that heat, it immediately dissipates to the air above. That's why we add acid to the top of water, not the other way around. Okay? And if you remember, well, the safety video just made it look like it stirred. Yeah, the safety video was stupid. Okay? It largely comes down to scale and concentrations. Usually at the scale that you work with, you're not going to generate enough heat to cause a boiling process. So what we're trying to set you up with is the skill sets that would allow you to be safe if you moved forward. Okay? Our strong acids are so exothermic that we can get that explosion process. What's happening with our weak acids? Well, the weak acids don't form a lot of products. Why not? It's an endothermic reaction. Okay? And because it's an endothermic reaction, we don't produce as much products. We can look at our delta G's, we can look at our K's, and we can discuss now the stability of those conjugate bases. Okay? The stabilities of those conjugate bases, or the relative stabilities of those conjugate bases, are ultimately defined by the quantification of our Ka's and our delta G's. But that means we have to quantify the crap out of it all. Okay? That's your job in this class. You take OChem goes at it and looks at it and says, well, somebody did all that work. Can we come up with rules that would allow us to explain the stability of that conjugate base without having to look up a bunch of tables? And yes, moral of the story is yes, we can do that without having to look them up, which is pretty phenomenal because now we can predict a bunch of chemical reactions without having to run chemical reactions or use a calculator. Gotta love that. Unless you like math, in which case, sucks to be you. Make sense? Ish? Okay. KB is same concept as Ka, except we flip it on its head. Okay, so Kb is the equilibrium expression now for a base reacting with water. Okay, so if we're looking at this K, or this chemical reaction, because we're calling it a base, we're going to start with our base, we react it with water. What does the base do? What does the base do? It gains a hydrogen, so in the course of the chemical reaction, I need to repeat my B and give it an H next to it. The exact location of where that H isn't super important. Don't stress about that. If we start showing structures, you'll see me start placing it where it's really critically important to place it from an organic chemistry structural standpoint. You're not an organic chemist. You're not doing structure necessarily yet either. So try not to panic about that. I understand you want to learn more. Slow it down. Just put the H on there. Okay? Depending on the charge state of our base, if it starts neutral and it gains H+, we need to account for that positive charge there. And if we're now going to write out our K expression, it's the same K expression we would always do. We write out our products, BH plus times the concentration of our hydroxide over B. Why would we call this a KB? Well, we called it a Ka because the dangerous thing with our acids was H3O plus. What's the dangerous thing with our base? OH minus. So it's a Kb because I'm seeing OH minus up here in the numerator of my expression. why do I not call the K for water a KB? Doesn't it have the OH minus? Oh, I forgot. That clock is wrong. It does. Why don't I call it a KB? It has both. That's why we end up calling it a KW instead of a KB or a KA. Kind of, sort of? Okay. With that, because I just looked at the clock, we are done for today. Everything that we did for KA, you do again for KB. Okay? And it goes all the way back to the beginning that our KAs and our KBs are ultimately going to be related to each other because they're both tied to K for H plus and OH minus. And so all the stuff is giant web of interconnectivity. Right? And I intention to say this in the nicest way possible. Please continue to keep packing and leave. Right? But I am saying at the tutoring center, they do have a little worksheet that ties all of these things to each other in this, I would call, horrendous looking diagram where it says if you have pH, how do you figure out the Ka? How do you figure out the Kb? How do you figure out the pKb? And so it ties it all in so you can go all which direction and how you would go through and solve. Okay? I would argue that little sheet is going to be very, very helpful, particularly for Alex, and keeping track of all your different formulas.
You said it's in the tutoring set?